Okay, what this problem is saying is to evaluate the right Riemann sum as n approaches infinity for the function f of x equals x squared over the interval from 2 to 4. We're not supposed to directly integrate, which if we directly integrated, it would just look like this. And that's pretty easy to evaluate. They want us to show how we would get this whatever this answer is, using the limit of a Riemann sum as n approaches infinity. In order to do problems like this, you have to know some summation formulas for this problem, particularly these two. And you'll see that these are used on the next couple pages. Okay, there's additionals like the sum from I equals 1 to n of I to the fourth and even more. If we go to board 2, here's the graph of y equals x squared. And the idea is on the interval from 2 to 4, we're going to divide this into n rectangles of equal width, of width n, and then we're going to let the number of rectangles approach infinity. So n will get bigger and bigger, so the width of the rectangles will get smaller and smaller. So let's work on finding a formula for area of one of these rectangles. Okay, so delta x will be the length of one, or the width of one of these little rectangles. So we'll divide the interval from 4 to 2 into n rectangles of equal width. That means the total length is 4 minus 2, and divided by n, that'll give us the width of each little rectangle. Now, to get the right-hand endpoints, think of it this way. We're going to start at the number 2, and to get the first right-hand endpoint, we're going to add on one of these widths. That takes us to the right-hand endpoint of the first rectangle. For x sub 2, we add on 2 of these widths. And then in general, to get the right-hand endpoint of the ith rectangle, we add on I of these widths to the starting point 2. And this simplifies to 2 plus 2i over n. Now, how do we get the area of the ith rectangle? Well, we take this number, plug it into the function x squared. That's what this is right here. That will give us the height of the rectangle, or the length. And then if we multiply that by the width, we will have the area of the ith rectangle. And if you square this binomial and then distribute the 2 over n, this is what you end up with. I'll let you verify that. Okay, and now we're going to add up all of those rectangles using summation notation. So here we are on board 3. Here is that formula for the area of the ith rectangle repeated. And now we're going to sum these areas from 1 to n, whatever n is. N could be 1,000, n could be 1,000,000. We're eventually going to let n approach infinity. But using summation formula theorems, we can break the summation of this entire thing into separate terms. The sum from I equals 1 to n of 8 over n, of 16i over n squared, of 8i squared over n cubed. And now any expression that doesn't contain the letter I is a constant. So another summation theorem is that I can put the constants out front of the summation notation. So here I've pulled out an 8 over n. I've pulled out the 16 over n squared and the 8 over n cubed. And now we have formulas for each of these guys. The latter two are on the first board. The sum from I equals 1 to n of a constant is just the constant times whatever n is. We're at, like adding up n of these constants. So this is replaced with an n. This summation notation is replaced with n times n plus 1 over 2. And the sum from I equals 1 to n of I squared is replaced with this These cancel. That leaves me with this 8 for the first term. If we multiply these together and write it over n squared, I'll let you follow along. This numerator here is the result of multiplying these 3 factors together and reducing 8/6 to 4/3, putting the n cubed under. And now we divide n squared into each term of the numerator. We divide n cubed in each term of the numerator. And finally, I introduced a limit as n approaches infinity of all of this. And so as n approaches infinity, these fractions approach 0. So 4/3 times 2 plus 0 plus 0. And that gives us 8 plus 8 plus 4/3. And if you get a common denominator and add them together, you'll see you do get 56/3. And if I go to the previous board, you can see that I did evaluate that here, even though we were told not to, using a definite integral. Same number, 56/3. Okay, there you go. That was a little long. Hope that helped. And if you have any questions, post a comment.